Namaste everyone. This is Vinay Kumar from Indian Institute of Remote Sensing. So today I am going to talk about hyperspectral remote. In hyper remote sensing, as you know, that is a definition is collecting information without being in physical contact with the object. And the two important thing in in remote sensing is spectral reflectance curve of any feature. If you have to identify any of the material, you have to have some knowledge of spectral reflectance curve of that material, and that spectral reflectance curve is when it is in detail, when you have more number of bands, then you'll be able to get better spectral reflectance curve of the feature. So here the name is hyper means excessive, and spectral is related to your wavelength. So when you have excess information in spectral range or wavelength information and used for remote sensing application data acquisition, then that is called as hyperspectral remote. So in this particular talk, I'll be covering this particular things, that is data availability. So what are the data, where the means from where you can get the data sets, what are the data sources, then what is the data quality, means whenever you will download the data, you will see that when you have excessive number of bands, the data are affected with certain kind of noise. So how to deal with it? Then after, you have to go for pre-processing, you have to do certain errors correction, and you have to convert that ultimately to reflectance. And then as you have excessive number of spectral bands in the data, then you have to perform data dimensionality reduction, which is required, one of the essential step for end member extraction. And end member extraction is one of the step, like whenever you have to identify any unique material, you have to extract end members, either using your image, or you have to use instrument based techniques to collect the ground spectral reflectance curve. And then after, you have to go for the spectral mapping, and you can generate the unmixing, means weighted fractional coefficient of the image, because when you have multiple bands, you can, means more number of spectral bands in a mixed pixel, if you have some features, you can tell the fractional coefficient of those features. Then what we can do is, we can even perform enhancement by fusing the data with some of the other sensors data to enhance that details. So these things I am going to cover in my talk. Now you can see, as I told, spectral reflectance curve is important. So to differentiate three major land cover features: water, vegetation, soil, your multispectral data is good enough. You can see here, spectral reflectance curve of water is how it is high, some value in blue, high in green, dip in red. When it reaches towards infrared, it is zero. In vegetation, it is high in green, absorption in blue and red, and very high in near infrared, and two absorption band in 1400 and 1900 nanometer. And here you can see soil, dry soil is having a kind of constantly increasing and reflectance curve. So here three major land cover features can be differentiated. So we can identify this is water by knowing that infrared is having absorption. We can know this is vegetation by knowing infrared has high reflectance, red has absorption, and these two absorptions you have to understand. So on the basis of that, these land cover features can be identified. But if the vegetation features, like we can only visualize three bands at a time in a data. So all the vegetation features, suppose if you are using FCC, all the vegetation features will appear in red color. And if you are visually seeing your vegetation leaves also, all vegetation features are appearing in green color if it is healthy. So how to differentiate that which vegetation feature is what kind of species? And if suppose you have to identify that different particular material, or even you have to identify different minerals, so here you can see there are this particular spectra of two minerals, hematite and goethite. So in this, if you have to identify these two minerals, this particular absorption features can be detected, and you normally this earth surface materials have diagnostic absorption features in this visible to reflected infrared rays. So on the basis of spectral resolution, your data sets are categorized into three major categories: panchromatic, multispectral, and hyperspectral. Panchromatic is a single band ranging in visible to near infrared or only visible range. Multispectral tens of bands are there, and broad discrete spectral bands are there: blue, green, red, near infrared, and short wave infrared. But hyperspectral will be continuous. So because of the continuous spectral bands, you are able to get reflectance curve in more details, which is helpful for identification and differentiation of the particular material. So how we are doing that? So spectral resolution, first you have to understand. Spectral resolution normally is defined by a normal distribution curve that is called as spectral response function. So normally what happens is, in this case you can see this is a normal distribution curve, and the wavelength range is from 0.4 to 0.7. But I want to know what is the detector response, means what should be the wavelength range for a detector. So normally it is defined by full width half maximum. Full width means the full width of the spectral response function, where you have 50% of the response. So this particular range is actually the detector's response range, that is ranging from 0.5 to 0.6. And this full width half maximum is the spectral response function, or means you can say detector wavelength range. And sampling interval means when you are taking the measurement for two different response, so that is called as sampling interval. So here you can see the spectral response function for multispectral and panchromatic is, you can see this is for blue, green, red, and near infrared. So you can see here it is discrete and separate with other bands. Only in blue green you are seeing a little commonality between the two bands, that they, whenever you draw the full width half maximum, there will be a little overlap. But here you can see in panchromatic, this is covering a full wavelength range from visible to near infrared. So in multispectral there are gaps. But whenever you will see the spectral response function of hyperspectral, when you will draw the full width half maximum, you will see there is no gap in between the bands. So for each band, you are getting the spectral reflectance curve. So those spectral reflectance curve will be in more detail. How? You can see here, this is a multispectral data with 6 bands. This is a multispectral data with 9 bands, and this is hyperspectral data with 150 bands. So here we can plot the nature of the feature, like this is a vegetation. Little more detail in 9 bands. But when we took hyperspectral, you can see the absorption in between the wavelength range is also coming into picture, which is able to differentiate that material. So multispectral will have discrete bands and hyperspectral will have continuous bands. So normally we have to think that how we are going to get this many number of spectral bands from the when the data acquisition takes place. So in multispectral scanner, normally the detectors for blue, green, red, near infrared are different. But in this case, for doing the spectral separation, we are using a different kind of technology. Like in school time, you might have done the exercise, like you have used a prism. Using a prism and you pass a monochromatic white light, spectral separation will take place. So here also similar kind of technologies are being used, like here from prism monochromatic white light passed and spectral separation took place. So there are many kind of similar instruments are there which are used for spectral separation, like prism base, grating base, West base filters are there, for Fourier transformation filters are there, which are used for doing this kind of spectral separation. So hyperspectral normally involves acquisition of image data in many contiguous spectral bands, and normally producing laboratory quality reflectance spectra. So once the data is converted to reflectance, you can see here that this is XY is representing the spatial information, and this Z is representing spectral information. For this pixel, when we draw the in x-axis, this is the wavelength and this is the response of that. So this is going to show you a kind of reflectance spectra which is similar to your laboratory quality reflectance spectra once it is properly converted to surface reflectance. So normally, because we have hundreds of bands in this data, so this is also called as data cube. So it is actually the important thing here is, if suppose you are covering full entire wavelength region visible to reflected infrared, so the spectral bands will be more. But in case of hyperspectral data, the important thing is the narrow bandwidth. Narrow bandwidth, when you have very narrow bandwidth 5 to 10 nanometer, that comes under hyperspectral. Suppose you are using only particular wavelength region, green, blue, or red, or any of the wavelength region, So in that wavelength region, whatever, if you have 5 nanometer wavelength spectral bandwidth, and you have only 20 bands or 15 bands, so that also comes under hyperspectral. So narrow bandwidth of the data is important. So because of ample spectral information, we are able to actually identify and distinguish spectrally similar material. And here you can see, when we try to visualize the FCC, you can see here we have used band 40, that is near infrared through red, then band 30 red band through green, and band 20 green band through blue as your standard false color composite. So you can see here the number of band means the near infrared band position is where. But if I am talking about multispectral, the combination for generating FCC will be 432 or 321, or any of the band combination, that depends upon the number, but it will be in the tens of band only. But in this case, you can see the number of the bands is comparatively higher. Now coming to the different hyperspectral sensors. So hyperspectral sensors are categorized into airborne, spaceborne, and ground-based. So airborne sensors are HIMAP, AVIRIS, HIDICE, digital airborne imaging spectrometer. There are many airborne hyperspectral imager. ISRO and NASA collaborated, and AVIRIS next generation mission was flown over main various sites in India and have acquired data. So the data sets are available, you can use for your applications. Hyperion is the sensor which was launched from NASA. CRIS is from European Space Agency, that is in Proba 1 satellite. HISIS was launched from ISRO. Prisma was launched from Italian Space Agency, and NMAP sensor was recently launched by your German Space Agency. Ground-based sensors are your spectroradiometer, which is used to measure the spectral reflectance curve of any feature, which is with very high spectral resolution. And hyperspectral future missions are there: GISAT with hyperspectral VNIR, and hyperspectral SWID with 320 and 192 meter spatial resolution. HISPRI is going to be launched from NASA. Hypersat will be the commercial constellation of satellites, which will be available with 200 plus bands with 10 meters spatial resolution. So this is the specification of different airborne sensor. Normally the major evolvement happened when AVIRIS sensor came into picture. So AVIRIS sensor was launched from JPL, that is Jet Propulsion Laboratory, and with a purpose to for mineral identification and mapping. So earlier it was with 220 spectral bands and 10 nanometer spectral resolution. Then compact airborne spectrographic imager came. Then after that, it was in the visible range, VNIR range only. Then shortwave spectrographic imager also came, and thermal was also launched by your Canada. So they are your airborne instruments, and in most of the cases you can see it is covering the wavelength range from 400 to 2500 nanometer. Only in some of the particular sensors, they are not considering the water absorption band, which is in the 1400 and 1900 nanometer range. So, and in most cases, the spectral resolution is very narrow. In some of the cases, spectral resolution is varying, it is not fixed. And spatial resolution is varying because it is in the airborne platform, so we can fly it at different altitude, and we can get the good resolution data as well. Now coming to AVIRIS next generation sensor data. So this is one of the sensor. So if you compare with AVIRIS, in AVIRIS it was with 220 bands and 10 nanometer spectral resolution. But in AVIRIS next generation mission, it is 425 and 5 nanometer spectral resolution. And you can see here, this is the one of the example image of Buxar area, Ganga river. So here you can see clear water and turbid water was acquired. So you can see the reflectance curve went up when there is a drainage opening here. So that you can see how the turbid water reflectance is coming, and we have collected ground spectra also. So they gave similar kind of response with clear water and your turbid water. Then these are the spaceborne hyperspectral sensors. In case of spaceborne hyperspectral sensors, Hyperion was one of the sensor with 400 to 2500 nanometer spectral range, and with 220 spectral bands and 10 nanometer spectral resolution, and 30 meter spatial resolution. But swath width here was 7.5 kilometer. So a very small portion was covered when the data was getting acquired. It was following Landsat 7 ETM plus 7 satellite 1 minute behind. So that's in the similar geometrical condition the data was acquired. Now coming to the other sensors like MARIS, MODIS, these are used for the atmospheric applications and all. And in this case, the number of bands were less and spectral resolution was high. Then compact high resolution imaging spectrometer. This particular sensor was having one additional capability, that is multi-viewing capability. It can acquire data at 5 different viewing angle, plus 55 degree, plus 36 degree, 0 degree, minus 36 degree, and minus 55 degree. And here it was the inherent capability of this particular sensor was with 64 bands, but they increased the spatial resolution with 80 meter and the reduced to 18 spectral bands. Then HIC on IMS-1 satellite was there. HICIS, which was launched from VNIR. So HIC was with very coarser resolution, and similar sensor was kept on Chandrayaan-1 satellite, and with a greater spatial resolution, as altitude is one of the factor which is playing a role. So earlier the spatial resolution was 550 meter for HIC, and in case of Chandrayaan-1 HIC, the spatial resolution was 80 meter. Then HISIS was launched recently in 2018, and it is with 60 spectral bands in VNIR, 256 in SWIR, and 10 nanometer spectral resolution. Spatial resolution was 30 meter, and swath width was 30 kilometer. Then Prisma sensor, which was launched in 2019 by Italian Space Agency. So it was with 400 to 2500 nanometer spectral range with 237 bands and 30-meter spatial resolution and 30 kilometer swath width. And InMap, which is recently launched with a little varying spectral resolution and 30-meter again for spatial resolution and 30 kilometer swath width. So this is launched in 2022 only. And Chandrayaan 1 High C, as I told, the similar sensor was flown in IMS-1 satellite. Chandrayaan 1 Moon Mineralogical Mapper was with 400 to 3000 nanometer spectral range. And Omega sensor and one more Chrism sensor is also there, which was in your Mars reconnaissance orbiter. Then MOM was with thermal sensor. So they were used for identification of minerals in the Mars surface. So this was your EO1 Hyperion data. So this data you can see, this is from Rishikesh and nearby area. So here you can see this was launched in 2000 with this is the range 0.4 to 2.5 micrometer, and this is the example image of this is the sensor, Hyperion sensor, and radiometric resolution for this was 12 bit. This is some examples of HISIS images, and this is the specification. As I told, it's a VNIR with 60 and 256 bands for SWIR, and 30-meter spatial resolution and 30 kilometer swath width. These are the future hyperspectral mission which will be launched from European Space Agency, France, NASA, and is Israel or Italian Space Agency, that is Salom. So this is the spectral range. You can see the spatial resolution will be a little coarser, and here you can see this with the sensor which is going to be launched from France will be with 8-meter spatial resolution. HISPRI will be with 60-meter, but swath width here it will increase. So if you remember, Hyperion sensor was with 30-meter resolution with 7.5 kilometer swath width, but here it will be with 145 kilometer swath width, and more than 200 spectral bands will be there. Now coming to the data quality of hyperspectral data sets which was acquired. So normally what happens is whenever we will talk about spatial noise, this hampers the visual image interpretation. But spectral noise actually hampers the spectral absorption which is used to identify any feature. So if blurs the absorption feature, so it is going to be difficult to identify that. And because what we have to do is we have to match this absorption from your ground measurement. So if it is the absorption are hampered, it hampers the statistical calculation as well. So what are the sources of noise? So normally sensor drift, whenever after some time, normally the sensor deteriorates. Then signal conversion, dn to radians, radians to reflectance. So while converting also, or analog to digital conversion is happening, then also this problem occurs. Electronic vibrations and moving parts in the sensor also cause. Platform vibrations, especially aircraft engines, also can cause noise. And irradiance variation, like from morning to noon, or from morning to evening, or from different weather condition, your solar energy is changing, so they also cause variation. Atmospheric attenuation, because of scattering and absorption, also can cause this issues. Then atmospheric path radiance, like because of atmosphere path, whenever incident energy is coming, it is scattered and it is going to the sensor directly, so that is also causing some of the error. So here, how to fix this error? So normally what we have to do is, like here you can see band 1 and band 242, because what is happening, whenever you will download the data, we have two different detectors for VNIR and SWIR. This is the example of Hyperion sensor data. So some of the overlapping bands are there, so that's why the number of bands are more, 242. So those overlapping bands you have to discard. First few bands, as they don't have separate detectors, so some of the bands will contain no information. In the water absorption bands also, so no information is getting acquired, and some of the stripping or drop line errors are coming. So normally this drop line errors we have to correct by running a mean filter, or you can take the average of neighboring pixels and we can replace the entire line. Then if you have to reduce the noise, one of the data dimensionality reduction technique is there, that is called as minimum noise fraction. So by using that also we can reduce the noise for a larger extent. So how we will do, I will be explaining that in my data dimensionality reduction slide. So this is the entire hyperspectral data processing. Normally, whenever you will download the data, you will see that your data is in radiance form. So you have to convert that to surface reflectance by performing atmospheric correction. Then after performing atmospheric correction, you can go for data dimensionality reduction. And after data dimensionality reduction, you can go for end member extraction. And if you have spectral library, you can use the same spectral library, you can classify the data, and using the same data even you can do the unmixing. So this kind of spectral library or end members will be generated from the hyperspectral data. So how to perform atmospheric correction? So actually there are two ways, two approaches, empirical and absolute. So normally in empirical approaches, these are the relative methods. So this will give you relative reflectance. Means suppose the data is given to you and you don't know any of the parameter, and you have to convert that to surface reflectance. So what we have to do is image based method you have to use. So in flat field, what we have to do is, normally to convert to reflectance we require two measurement, radiance and irradiance. So in flat field, first what you have to do is you have to identify a flat field, means which is a bare field. Normally those features are highly reflective. Take the average pixel value of that flat field and divide from each and every pixel. So that is your flat field method. In internal average relative reflectance, what we have to do is you have to consider whole image. And one main assumption for this is, what you have to, this particular technique will work best when there is no vegetation. So take the average of complete image, divide from each and every pixel, that will be IIRR. And coming to empirical line calibration, in this case what we have to do is we require two ground measurements, dark for dark feature and for bright feature, and you have to solve a linear equation, that is y is equal to ax plus b, where x is the radiance, y is the reflectance collected from ground. So for dark also you have to take the equation where x and y is known, and for bright also y and x is known, and then you have to calculate a and b. Now knowing a and b, you have to substitute in the same linear equation y is equal to ax plus b, and in x you have put entire data. A and b is now calculated from by solving dark and bright values equation, and you will put the a and b value and you will get the converted reflectance data. In case of absolute reflectance correction, normally what we are doing here is we have to use radiative transfer model, and this radiative transfer models requires many measurements. This requires atmospheric condition, water vapor condition, aerosol condition. You have to know the scene sensor geometry, date and time of acquisition. So by knowing all these parameters, you can convert this to absolute surface reflectance. So here, this is the example of converting it to absolute surface reflectance. Here you can see this is your FCC of Hyperion data. This is your radiance spectral profile. This is your reflectance of vegetation, dry riverbed, and water. So how, after converting it to reflectance, how the radiance has converted, you can see in this three profiles. So after converting it to reflectance, then we have to perform geometric processing. So if it is not geometrically corrected data, then how what process we have to perform? So normally you have to do the geocoding, like you have to provide positional information, GPS and aircraft altitude. You can correct the data. But normally, Earth's surface is not flat; it is undulated. So you have to use DEM for converting it to ortho image, generating it to ortho image. Why it is required? You can see there is difference in pixel size and location error is coming. So because of that, we have to convert that to ortho image. So after getting the pre-processing of the data, then we have to perform data dimensionality reduction. So why it is required? So normally it is required to subset the spectrum of interest, to reduce the computational overhead, because when you have more number of spectral bands, then it is going to be time consuming process for processing the data. It will take a lot of memory also for processing this data. Third reason is it will reduce the noise and improve the signal to noise ratio of the data set. So here these are some of the data dimensional reduction technique, that is PCA, MNF, and independent component analysis. So normally principal component analysis we are performing by translating and rotating it to near axis, which is going to provide the maximum variance of the data. So here you can see this is one of the data dimensional reduction technique, PCA. So here first few components will contain maximum of the information and then followed by your noise. But in PCA there is a problem is what, like what is happening is whenever you will convert or perform the data dimensional reduction, it will translate and rotate to a newer axis and maximum variance data will be collected, but it will not bother about the noise content present in the data. So what is happening when you will perform, you will see that few components will be informative, then all of a sudden noisy component will come, then informative component will come. So because of that, we have to think of other alternative so that we can perform the data dimensional reduction, that technique which will follow the same trend, like first component is informative, second, third, and as a number of component will increase, the noisy component will come. So here you can see this is one of the data dimensional reduction technique, that is MNF. In this case, MNF1 is informative, second, third, fourth, fifth, and as it is the number is increasing, noise is coming. So in this case, what is happening is we are applying PCA twice. First, to reduce the noise component, and second we are applying to generate the uncorrelated component. Now in this case we are using a shift difference method. What is shift difference method? In this case, normally we know that nearest neighbor pixels will have similar values, but the noise content will vary. So we are using the image differencing method, like neighboring pixels will be differentiated, and the difference will be calculated. So that difference, that's why it is called as shift difference. It is shifting to neighboring pixels and calculating the particular noise amount. So those noise amount will be segregated, and then after in the noise reduced data, the PCA is performed to get uncorrelated component, which will follow the similar trend, that first is informative, then second, third, fourth, and so on. Third data dimensional reduction technique is independent component analysis. In this case, what is happening? The first two dimensionality reduction technique works on second order derivatives. This works on higher order derivatives. In this case, independent components are extracted, which is some of the features which cannot be differentiated or identified to your first order or second order derivative. Then your higher order derivative will help to identify that. So in this case, higher order derivative like skewness and kurtosis are being used to extract them. So in this case, you can use a simple example. Normally what happens is, whenever you are in a crowded place and you are listening to the sound, somebody known to you will call, then you will be able to separate that particular sound. So that kind of principle is applied here. If you have to separate the individual signal, so you have to use the higher order statistics here. So in this case you can see that different features, like in this case scrubs, in this case some type of vegetation, that grassland, urban, here your some other kind of vegetation, agriculture field, then here the vegetation. So different kind of features are differentiated here as you are seeing the different independent components in this case. Now coming to the extraction of end members. So how to extract end members? So normally you can go to the field, you can have your spectroradiometer, you can create your own field or lab measurements. You can bring samples from the field, you can measure the spectral reflectance curve from those instruments. So this is a kind of one instrument, spectroradiometer. I will tell you how this collects the data. And then second is either you can use spectral library collected already or prepared by some different laboratories. So in NV software, publicly available spectral libraries are there. Aster Spectralib is also available on the internet. USGS spectral library is also there. Then from image also you can extract. So this is actually the end member extraction process. First is MNF. So why we are performing MNF? To reduce the data dimensionality reduction. And second, whenever you are going to see the first MNF component, it will have high SNR. So the high SNR components we are considering here for that process. Second is what? PPI and ND visualizer. So that we have to perform for extracting the end members. I will tell you how PPI and ND visualizer is performed. So here you can see this is the spectral library collected from the spectroradiometer used here. So how the spectroradiometer collects the data? First is the instrument should be warm enough before taking any measurement, and normally the instrument should be charged before going to the field. So in this case you can see there is a laptop connected with this spectroradiometer, and she is holding a pistol. This is called as fiber optics, which is connected with this spectroradiometer. This particular plate is white reference plate, or you can say this is as spectralon. This is 100% reflective in the visible to reflected infrared region, and this is now targeting to the sample. So to collect the spectral reflectance curve, we require two measurement, in, incident energy, or you can say irradiance and radiance. So normally getting irradiance you have to use separate instrument, or you can use this kind of plate for getting the 100% reflective information. So first, the process for collecting that is what? Dark current measurement, white reference measurement, and target measurement. Dark current measurement means what? Normally, whenever any electronic device is there, if you even after you are not using it, some electric current is flowing inside it. So that will be added to the signal. So that needs to be discarded first. So that's why first you have to go for dark current measurement. Second is then you target it to white reference, which is this. This particular material is made up of polytetrafluoroethylene and centered halon. Then after you can go for target measurement. So here you can see these are the spectral reflectance curve collected from this instrument. In 1400, 1900 and 2500 nanometer, you can see atmospheric absorption. Then after, as I told, end member extraction, the second, the other steps for that is what? First we did MNF. Then after you have to perform PPI, that is pixel purity index. In this case, what is done is you have this particular step will try to identify most spectrally pure pixel location in all over your image. So wherever this white color is there, you can see these are having some values for different features. So these are your pure pixels which are identified. Wherever it is 0 or dark, this may be your mixed pixel. Now when you have extracted this particular pure pixels, these pixels you have to plot in ND visualizer, that is n-dimensional scatter plot. So here in this case you can see these are the ND control. Here you have different number of components which are kept. So whichever pixels which are coming at the extreme, they are extracted. So here you can see, suppose these are three components and these are the pixels present in that. This particular pixel are going to exist at the extreme. So that's why they are called as end member. And even you can see, if suppose you are just consider a feature space, between near infrared and red, you just prepare a scatter plot. And if you have water and vegetation feature, so water will lie where? Water will lie in the lower value or in near infrared, and little value in red. In case of vegetation, very high value in near infrared and low in red. So both the two pixels will appear at the extreme in case of water and vegetation. So similarly, if the features are different and unique, they will appear at the extreme, and that will be extracted from the particular ND visualizer. So here, after performing this particular end member extraction step, you can see this is the scatter plot with 15 components. We move the scatter plot number of times, and you can see wherever the pure end members were there, they were extracted. And here you can see where these end members are lying. So I have extracted here almost 6 classes. We can extract some more. So these 6 end members were extracted, and in form of spectral library, in form of region of interest are extracted. Using that, you can perform classification and or unmixing, or whatever end members you have extracted, you can go to the field, you can cross check it, what features are this, and you can rename this end member. So once the end members are extracted, now we have to perform classification. So classification techniques for hyperspectral data is little different than your multispectral data. That is spectral angle mapper, spectral feature fitting, or linear spectral unmixing, mixture tune match filtering. They are your unmixing technique, or you can say weighted fractional coefficient images we can generate through this two techniques, or subpixel techniques are. These are the subpixel techniques. So in case of your spectral angle mapper classification, normally this is considered as spectral similarity measure technique, where we are trying to match your image spectra with reference spectra. Here reference spectra, ASD spectrum is written. ASD means analytical spectrum device, which is the model name of spectroradiometer. So earlier the format for that ASD spectrum was .ASD, so that's why ASD spectrum is mentioned. So whichever spectroradiometer spectra is there, so you try to match with that using one of the parameter angle, spectral angle. So how to calculate the spectral angle? You can see this. So normally what happens here is, normally to calculate the angle, we are using the particular reference spectra and target spectra in form of vector. And here you can see this is representing dark, this is representing bright. And we are calculating angle between the two different features. So here suppose this is your phi, this is your phi. Angle, spectral angle was calculated using this equation. So this is your image spectra. So what is happening in this case, there is one advantage is, first is what? Minimum the angle, it will classify that feature. Second advantage is what? This is insensitive to illumination variation. If suppose this is a hilly area, this particular area is illuminated, this particular area is shaded, and you have your sensor is nadir viewing. So same of the two features are there. So what will happen? The feature which is in the illuminated side will have high reflectance, so high magnitude here, and feature which is in the shaded side low reflectance, so low magnitude here, but it will lie in the same vector position. So that angle whichever will be calculated will go to that particular class only. So here you can see this is a image with variation in the illumination, and this is spectral angle mapper classification performed, and this is with maximum likelihood. So in maximum likelihood, you can see the misclassification or unclassification is happening. And normally whenever you will perform this classification, you will get two types of output. One normal colorful classified output, and along with that rule images will be generated. And in this case, please remember, darker the pixels, better is the match. So here the grassland is there, here this is near to FRI, so here more grassland features are there, it is darker. In this case, this area is urban, so this is darker, and near to FRI forest patch is there, so you can see this is appearing darker. So dark pixels better match, or you can say more similar in case of spectral angle mapper. Then this is your spectral angle mapper classified image. So this is when we took the angle 0.02 radians, when the angle was taken 0.05, when 0.1. So you can see minimum pixels got classified. Here also you can see some of the pixels are unclassified. Here most of the pixels got classified, but few misclassification is happening. Here you can see misclassification is happening when you increase the angle. So even there is a limit, normally we have seen that 0.1 is considered to be good for classifying most of the field. So this is the same technique used for classifying ALI data and Hyperion data. You can see how the classification. So in multispectral, little misclassification is occurring, but in hyperspectral data, you can see species level you can classify in this. Now coming to the spectral feature fitting, in this method, normally what happens is we have to match the shape of the absorption and depth of the absorption. Once the depth and shape will match, it will go to that class. So here you can see this is a Everest image of Nevada cuprite area, and this is the root mean square image. So when we have to identify alunite here, so wherever alunite was there, it highlighted. This is considered as bright as good fit and dark is bad fit. So this pixel spectra, target spectra match the depth and shape. It highlighted that particular material. Then we can apply other techniques as well, like this is using pixel based technique. When we perform, this is a close range hyperspectral data, and this is a data with performed with object based classification. So with object based classification, you can see the pixels here which is getting mixed with other class, only highlighting that particular class. It is the mixing of between the pixels got reduced by using the object based classification. Then what we can do is we can perform rule based classification, like you can integrate thermal data also. So this is a data from Ahmedabad area, and here you can see this is data which is with similar reflectance curve with concrete and GIC, and this is a data with water and asphalt, means your shadow area. So this is having similar reflectance curve, but the temperature here you can see for water it is less, for this area which is urban area which is in the shaded side. So this is with high temperature. Concrete has lower temperature compared to your GIC. So when we integrated thermal data, you can see the improvement happen. So how the improvement happened, you can see this area is actually Sabarmati river front. So this was actually your concrete, but it was going as GIC. So when thermal data was included, it got improved. In this case, some of the pixels are having water pixels coming. So this also further got improved when thermal data was. Then coming to the spectral unmixing. So for spectral unmixing, you should understand spectral mixing for a single pixel. So normally pure pixel is a pixel when you have only one single class, and mixed pixel is when you have more than one class. So your mixtures are also of two kind, linear and non-linear. You can see when the incident energy is coming and separate energy is going, that is your linear mixture. When the incident energy is coming and the mixture is intermixed, then combined response is going, that is non-linear mixture. So what is happening, how hyperspectral data is able to identify this mixed material in the mixed pixel? So normally what happens here is, you can see this is your mixing space, okay, and here you can see this is a mixed pixel where three features are there, A, B and C. A is with 25%, B is with 25%, C is with 50%. So when we plotted the spectral reflectance curve of A, the absorption is coming here in this wavelength position. In B, the absorption position here it is coming. In C, the absorption feature is coming here. When we saw the spectral response of this particular pixel, you can see the spectral reflectance curve something like this. So whichever particular material is more dominant, the absorption for that was more dominant. So by seeing this particular mixed pixel spectra, we can identify, we can tell these features are present. So linear spectral unmixing, how we can do is, this is a kind of, we can consider each pixel is the sum of whatever features present in that area. It may be 0% or it may be 100% or it may be in between that. So the weighted fractional coefficient image will be extracted. So here wherever water pixels are coming, it got highlighted. Wherever scrubs are there, it got highlighted. Then grassland is highlighted in this case. The vegetation feature, that is your sal forest, is highlighted. Then dry riverbed. but here you can see dry riverbed and urban are having similar material, so that's why they are appearing bright. But wherever those pixels are with that contribution are highlighted. So it may be with a higher score, it may be means whatever percentage of that feature is present is coming over here. Then another technique is there, that is mixture tune match filtering. So in this match filtering, what is happening is, suppose this is a partial technique, where whatever end member you are going to extract, you can only give that end member and it will highlight the feature, and remaining feature will be suppressed. So match filtering is working in that concept. Suppose you have a filter, and whatever filter size, kernel size is there, only that kernel size, those particular material will be filtered out, rest of the things will be discarded. So in this case, whatever end member you will give, it will match with that end member, and it will highlight the response of that end member, and other end members which are in the background, they will be suppressed. So this will give the grayscale image, score image, which is ranging from 0 to 1. 1 is better match, 0 is no match. But sometimes what is happening, like here in this case, you can see this urban area and dry riverbed came as similar. So one additional parameter is added in this mixture tune match filtering, that is called as invisibility, which only highlighted that feature and to discard the mixed feature. So in this case, we took high score and low invisibility value, which only highlighted the urban area, discarding the dry riverbed, which was also appearing bright. In this case also, whatever vegetation feature we wanted to highlight is coming here. You can see with another example, this is your MTMF score and invisibility image of your vegetation. So wherever vegetation is highlighted, and the other features in invisibility image, it is appearing. Then as I told that we can perform resolution enhancement. So resolution enhancement we can perform by either by fusion, or there are techniques that is called as single frame super resolution. Using that technique, the bands itself, we can perform some of the image processing, and then we can enhance the data. So here you can see that after performing the super resolution technique, here this is the nearest neighbor resample data. The data is with 8 meter. We resampled it to 4 meter, and super resolved output of 4 meter. So here you can see the texture of vegetation is coming properly. Here you can see the edges of roads are coming properly, and this edges of buildings are also improved. So this improvement happened with super resolution. And we also observed that when we classified the nearest neighbor resample data, the soil is mixed with other material, but it was actually soil. You can see there is a bare ground, and it got improved in the super resolved. Then as I told about fusion, so you can because we were having ALI panchromatic image with 19 spectral bands in the common wavelength region, that is invisible to near infrared. So we took that 19 spectral bands and we fused it from 30 meter and we generated to 10 meter. You can see this urban feature got improved here, and spectral reflectance curve was more or less similar after the fuse. This is the fusion of hyperspectral and pulsar data for enhanced land cover mapping. So what we can do, even what you can fuse this particular hyperspectral data with SAR data also. So here we tried to fuse SAR data with means radar set 2 data, fully polarimetric data with Hyperion, ILOS pulsar data with Hyperion, and with different label also, pixel label, feature label, and decision label. And here we observed that feature label performed better in case of hyperspectral and ALOS pulsar data, and it also improved the classification of the fused in the fused integrated output. So these are few of the applications which is used for hyperspectral remote sensing. So vegetation, soil studies, mineral mapping, water quality, snow grain size, and urban studies. So for vegetation, species level vegetation mapping we can do, even the health of the vegetation we can map. So with Hyperion data, what here you can see mixing of the classes happening here. We were able to separate out properly the vegetation species, and the accuracy was also better in this case. So why it is happening, you can see the spectral reflectance curve are appearing more or less similar. But in this case, you can see there are variation in the spectral reflectance curve of the multiple features present in that area. Then coming to soil studies, we can go for different type of soil studies like dry soil, wet soil, the moisture content we can identify. Different organic matters are affecting, so that also we can identify. So here you can see this is the classified image of your using your hyperspectral data, every cng data of ICRISAT area. So when we took reflectance data, little mis classification was occurring, but as I told, MNF improves the SNR and it discards the some of the noisy bands. So here red soil and black soil classification got improved when we used MNF based technique. Then this is your mineral mapping done through your Hyperion data, Pur Banera and Rampur Agucha mines for hematite and pyrrhotite and montamonite. How it got classified in this airborne in this Hyperion satellite data. Then we performed this in Cuprite, Nevada area, Abiris NG data, Kasi and shortwave spectrographic imager data. So, when we generated the abundance image using the spectral mixing technique, it highlighted those minerals properly. Like this is the alunite abundance image, this is dicite and smectite, and carbonate abundance image. But in case of compact airborne spectrographic imager, you can see only iron rich mineral got highlighted because it is good for highlighting that. As normally for mineral identification, we should use the longer wavelength wavelength range. So here you can see in shortwave infrared data, it highlighted most of the minerals, but FE reach was not able to highlight. When we used Everest NG data with all the spectral bands, you can see it tried to classify most of the features. Then we can use this for water quality studies. So in Chilika Lake Hyperion data, in the same time the spectral reflectance curve using spectroradiometer was taken, and here different level of turbidity was mapped and we validated with the turbidity meter. So here you can see that different level of turbidity was mapped so that water is of drinkable capability or not can be mapped, identified. Then we can go for snow grain size mapping. So this is the data from Nainital area. You can see with different grain size, snow reflectance is getting varied. And here with 50 micrometer, with 200 micrometer, 500 micrometer, 1000 micrometer, spectral reflectance curve is varying. So those fine grain, medium grain, and coarse grain snow are getting identified and mapped in this particular hyperspectral data. Then we can use it for urban material mapping. So this is one of the multiple end member spectral mixture analysis where we used automated end member extraction technique for extracting the end members. After extracting the end members, we tried to map this area. So here we saw that multiple end member spectral mixture analysis performed better compared to other unmixing techniques. So here you can see different features are classified properly in this data. Then what we can do is different softwares are there. IIRS Imagine are the commercial software, Multispec, BIM, Abhyas are the open source software. Limitations of hyperspectral data is sometimes fine atmospheric absorption features may be confused with ground material being imaged. Data volume, data size is very heavy, so average is 40 times thematic mapper data. Redundancy or overlap of information content over several bands are there. So thank you so much everyone.